Hello children, I am Prashant from Pragati the School. This is an online class designed for the students who are in 10th standard with Cbse or Karnataka SSLC stream. We are going to see physics chapter 13, magnetic effects of electric current. Before getting into the chapter, we need to understand what is a magnet and what is a magnetic compass. What is a magnet? Magnet, you can see here, you can see here also, it has got a two pole. One is north pole, other one is south pole. You can see a north pole and south pole. It has got a magnetic flux, the hairy kind of thing. What you're seeing here, what is seeing here and what is seeing here, it is a magnetic flux. Magnetic flux. And the lines what you're seeing, the small lines what you're seeing, see these lines, the small lines what you're seeing, which is emerging from north pole and terminating at south pole. You can see here it's going from north terminating at south. See here also starting from north and terminating at south. Okay, so these lines are called as magnetic lines or magnetic lines of force. Clear? So magnet has got north pole and south pole, and it has got a magnetic field, and always the magnetic lines emerge out from north pole and it gets terminated at south pole. Clear? And you can see the rules of magnet. You see the south pole and the north pole is getting attracted. That means it is an opposite side. If you see here, this is north side and this is south side. So opposite of south is north, opposite of north is south. So it has got two poles. So always if you take two bar magnets and keep it very close to each other, what happens? It attracts. When it attracts, when the two poles are opposite. See, if it is south, it is getting to north, and if it is north, it is getting attracted to south. Another thing, the same poles, you can see here the same poles repel. That means if north and north is coming very close to each other, it will go away or it will repel to each other. South pole is coming to near each other, it reflects, it pushes back, repels. Okay, that is the rule of a magnet. And what is a magnetic compass? What is a magnetic compass? Magnetic compass is a device used in navigation, and also it is used to detect the presence of magnetic field. You see here, this is a magnetic compass. Where is north? North is here, south is here, east is here, and west is here. And what is this dial which is oscillating here and there? That is a magnetic needle. It has got marking as N there and south S here. N means north, S means south. That means whenever the magnetic field is there, if the magnetic compass is kept in the magnetic field, the needle deflects. The needle deflects to the north of the magnetic field. North of the magnetic field. That we'll see in detail in the. You can see here. You can see here. This is called as a circuit diagram. This is called as a circuit diagram. It has got a battery connection plus minus, and it is connected to a key, it is connected to a resistor, and it is connected to a conductor, metallic conductor. What is metallic conductor? It can be aluminum, it can be copper, it can be steel, anything. A metal conductor is called as a metallic conductor. Okay, and it is connected to a negative side of the battery. This side is connected to the positive side and this side is connected to the negative side of the battery. The current flows from which direction? It always flows from positive direction to negative direction. I represents the current. Arrow represents the direction of current. That means it starts from positive and it ends at negative. See, whenever the current passes here, and if you keep the compass nearby it, what happens? What happens? See here, one example I am showing here. Battery is connected, positive is connected to the conductor, and negative is connected to the conductor. What happens when the switch is on? The current flows. Current flows from positive side. That means the current will start flowing from here, and it comes here, and it terminates here. If you keep on the top of the conductor or nearby the conductor, the magnetic compass deflects. When the current is flowing, it deflects. See here also, when the current is stopped, it becomes zero. When current is flowing, it shows zero. See, if you keep one compass at the bottom, its direction is opposite. If you keep the magnetic compass on the top of the conductor, it shows a different reading. That means the red part, if you see, it is coming to left. If you see the red part here, in this it is coming to right. Why? Because of the direction. Because of the direction, always the red portion is north, so it will always direct to the north pole of the magnetic field. So for example, if you change the direction, instead of plus, you can connect it to minus, and instead of minus you connect it to plus. What happens? The compass is deflecting in right direction. Now it will deflect at left direction. That's what. If you change the power, plus and minus, if you make it ulta, what happens? The deflection of the needle also changes. So that shows the magnetic field presence. So what we learn through this? We learn whenever a current flows through a conductor, the conductor becomes a magnetic field, or the conductor exhibits a magnetic field. Clear? So what is magnetic field? You're seeing this portion. See, there's so much portion you're seeing. All that lines, all that lines. We know what are these lines. These lines are called as magnetic field lines, or simply the field lines. See, where these magnetic field lines go, that portion is called as magnetic field. That portion is called as, see, up to here. See, this portion, total portion is called as magnetic field. Okay, this we know this is a bar magnet. North pole is here, north pole is here, and south pole is here. So whenever you keep the compass, the magnetic compass nearby it, what happens? See that red color indicates the north direction. So that north marking always will move the needle towards the north pole only, north pole of the magnetic field. That's what I explained in the previous slide. Understood magnetic field and magnetic field lines. So magnetic field lines always originate from north pole, and it gets terminated at the south pole. Be very clear whether it is anywhere. So 360-degree, this magnetic field lines will be coming. We are seeing only the section, that's it. But 360-degree, the magnetic field line will be available. See, from north it is coming to south. Clear? From north it is coming to south. So this is the magnetic field, and we have seen the magnetic field lines, and we know that always the needle in the magnetic compass always tends to move towards, shows the direction of the magnetic field in the north direction only. This concept should be very well understood. If you take a piece of paper, that means large piece of paper, and onto it keep a bar magnet, and over that you sprinkle the iron filings, iron powder. It is available in the market or in the lab. You can take that iron powder and sprinkle all over, like salt you sprinkle over the food. You have to sprinkle the iron filings over the bar magnet. How does it arrange? See, it arranges in different fashion. Are you able to see the arrangement here? See, it is having in some arrangement. You can see this picture also. You can see how it is getting arranged. It is arranged in some fashion. How, what fashion it is arranged? It is arranged in the along the magnetic lines of forces, along the magnetic lines of forces. Okay, and where the concentration is more, you can see more number of iron filings is attracted here north pole, and more number of iron filings is attracted at the south pole. Here also you can see south pole more number is there, and here also north so many iron filings is getting attracted. Why? Because that is the strongest points. That is the strongest points. Which are the points? North pole and the south pole. Those are the strongest points, and the magnetic force will be maximum at the poles, so that's why it gets attracted. And see here, always the magnetic lines of force start from north direction, and it pass on like this, and it ends at south pole. That is one thing. And you can see here, if you, without the magnetic compass, if you want to drain the magnetic lines of force, see, you have to draw like this, and again like this. How we will draw? Simply we cannot draw, right? While doing the experiment, it has to be done perfectly. We want to know how the magnetic field lines is arranged on a magnetic field. So how to do it? So we can keep a, see, these are the compass. We can change the position 1, position 2, position 3, like that, position 4, 5, 6, 7, different position you can keep this, and you can start marking the north direction. You can start marking the north directions. So it will be neutral here, and again it will start here. You can direction mark the needle directions, and you can just start drawing that, joining the lines. So it becomes the magnetic lines of force. It shows very clearly the magnetic lines of force. Like that, you can change the position of the magnetic compass and keep it at different position, and you can start marking the magnetic lines of forces. Okay, so this how we can find out through the experiment method the magnetic lines of the properties or the features of magnets. See, you have to see this very clearly. You can see this picture very clearly. See, all the 360-degree the magnetic flux will be coming. Okay, all the 360-degree the magnetic flux will be coming. And coming to the first property, magnetic field is a vector quantity. It has both magnitude and direction. We know scalar quantity and vector quantity. There are two types of quantities. Scalar quantity means it has got only magnitude. Magnitude means some value. Okay, it might be some force, it might be weight or something. Some magnitude should be there. So scalar quantity will have only the magnitude, but it doesn't have the direction. But magnetic field is a vector quantity. How to prove it? See, here already we have seen the magnet has got some force, right? It has got some force, magnetic force. It is force will be too much at north pole and south pole. Why? You're seeing so many lines which are coming out, which are coming in at the south and which are going out at the north. So that's why it will be very powerful at the poles. See, it has got a direction. The magnetic lines of force will start from north direction and it ends at south direction. That means direction it has got. So you can see here it has got direction. And what about the magnitude? Magnitude, already I told, magnetic field has got some strength. Because of the strength only it can attract iron filings or iron or some other magnet. So strength will be there. So magnetic intensity, that is called as the magnitude. So that's why magnetic field is a vector quantity. Next, the direction of the magnetic field is taken to be direction of north pole of the compass. So total, if you take the magnet has got the magnetic field. Magnet has got the magnetic field. Then when if you say the direction of the magnetic field means always it will be this direction. That means magnetic field always is reference with the north pole. We say this is the direction. This is the direction of the magnetic field. So that is important. Next, the magnetic field lines emerge from north pole to south pole. This already we have seen. See, it starts from north pole and again it terminates at south pole. Inside the magnet, how does it go? It goes from south to north. Outside, external, from north to, see, it is coming here and getting inside the south. So external it is north to south, and from internal it is south to north. Inside also the magnetic lines will flow. It flows from south to north. Okay, and the magnetic field lines are always closed curves. Already we have seen here, I just explained. So it comes up to here, north to south, and inside from south to north it passes, so it becomes a circle, it becomes a loop. So these are the 5 important properties which will be asking, which will come for the examination. And here the relative strength of the magnetic field is shown by the degree of closeness of the field. Relative strength, that means the strength of the magnet. How you define the strength of the magnet? If the magnetic field line, see here the magnetic field line 1, 2, 3, 4, 5 magnetic field lines are there, top and bottom also. How do you say it has got very good strength? If the magnetic field lines are very closer to each other, okay, if these are very closer to each other, then we say that the magnet is very very powerful, the magnet has got very high strength. That is the meaning of it. Second one, no two field lines will cross each other. No field lines will cross each other. You're seeing here everything is parallel, right? Nothing is touching each other. See, nothing is touching each other. Okay, nothing. Once it comes out from the poles, it never touches each other. That is the meaning. Touches means it never crosses each other, it never crosses each other. So these are the properties of the then magnetic field due to current carrying conductor. Already we have seen in the slide number 2 or 3 the same experiment. See, condition A and this is condition B. So in condition A, if you're seeing in this condition A, this is condition B. What is the difference? It is a battery is there. See, this battery is there, plus, sorry, plus minus. So the current flows always from positive to negative. We know I is represented by current. It flows and it comes through a conductor. So think that this one is a conductor. Okay, this one is a conductor. From here to here is a conductor, and it is connected to a positive from here and negative from here. Same thing here. And if you see here, the battery is connected negative this side and positive this side. Clear? And whenever you switch on the battery here, the key, you switch on the key here, what happens? The current starts flowing. And you can see the needle direction. The needle direction is like this. Needle direction is like this because current is flowing from left to right. Okay, then switch off. Then condition number 2, change the battery and connect ulta. So this side is negative, this side is positive. Then the current start flowing from positive, correct? Positive to negative, the current flows. And what is happening here? If you see, the needle direction is like this. Needle direction is changed. See here, this is from, it is showing right side and this one is showing as left side. That means the magnetic field changes when it changes the direction of the current. That you should remember. You can see here when the switch is on, what will happen? The current is flowing from positive and is terminating at negative. It changes. Instead of plus, if you connect at negative, and instead of minus you connect this one as positive, what will happen? The current will start flowing from this direction, correct? Then earlier it was, earlier the needle was deflecting like this. Now the needle will deflect in this direction, opposite direction. That is the meaning of it. Why? Because the magnetic field changes its pole. The north pole will become south pole, south pole will become north pole. That is the reason the magnetic compass changes its direction. Here also you can see here the current flows, this one will get deflected. The magnetic compass, that is a needle, will get deflected. It is deflecting in one direction. If you change the down, if you, that is the condition is shown for the downward current. If the current is going up, then the direction will change. Very very simple concept. change to a straight conductor. Already we have seen the same thing, right? In the previous slide, you can see here, you can see here, cell is connected and positive is here. So that's why the current is flowing from positive to, and it comes at negative. It is a conductor. You're seeing conductor is nothing but a thicker one compared to the wire. The metallic conductor will be thicker one. Then how the direction of magnetic field will be there? You can see the magnetic field will be in the clockwise direction. Clockwise direction, that means if the direction of current is from top to bottom, that means if you see from the top, that the magnetic field direction will be right side, clockwise, that is clockwise. It will be happening not only at this position, it happens at every position of the conductor. For easy understanding, we have kept a book, we have kept a small sheet of paper here, and we are showing here the cross section we are showing, so that it easily you can understand. But the same thing will be there throughout the conductor, every direction, every point, the same thing will be happening. Clear? And they will ask this diagram. See, this diagram is in the textbook. This diagram they will ask for 3 marks in the examination. See here, the condition, same condition. If the current is flowing from, if current is flowing from positive and it's coming up to here, and it is coming to negative, what is happening? You can see it is clockwise. That means the direction of current is from top to bottom. See, remember, from top to bottom it is coming. If you see from top, the direction of magnetic field will be clockwise. And see here, the battery is put ulta, that means it is interchanged. So negative will come here and positive will come here. Earlier it was negative here, positive here, correct? So the direction of current will be from bottom to top. From bottom to top, if you see from bottom, how does it look? It looks like this. That means anti-clockwise direction. So the magnetic field will be in anti-clockwise direction. You can see the electromagnetic is in clockwise direction, and here it is in anti-clockwise direction. So complex, you can see here, the compass deflection increases with increase in current. The complex, the compass deflection increases with increase in current. So if you increase the current, the deflection will be faster in the magnetic compass. Right hand thumb rule. So as per that principle, previous principle, if you see, this is true. So whenever you hold the, this is the direction of the current, correct? This is the direction of the current. That means current is flowing from this direction, and if you see, it is going in anti-clockwise direction. The magnetic field will be in anti-clockwise direction. So this is the picture. This is a picture you have to write if they ask in the examination. Simple, very very simple. Great. And magnetic field is inversely proportional to the distance from the conductor. Distance from the conductor. Say magnetic field. For example, magnetic field, I'll take it as M. Magnetic field is, this is a proportionality symbol. Inversely proportional means 1 by distance of the conductor, D. And here M is directly proportional to the current. If current increases, magnetic field increases. Okay, is magnetic field, if the distance is less, magnetic field is more. If the distance is more, the magnetic field is less. That's what this says, this formula says. These two things, these two concepts you should never. It is the same circular loop, right? And you can see here circular loops. See, the same thing has been clear. So please write 5 to 10 times so that you can understand very easily. Magnetic field due to a current in a solenoid. What is a solenoid? Solenoid is an electrical device. See, a coil of, 1 minute, I'll take a pointer so that it's easy for you people. See, a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. Very simple. See, it is wrapped, insulated copper wrapped closely in the shape of a cylinder. See, this coil is in the form of cylinder, this coil is in the form of cylinder, this is also cylinder, this is also cylinder. Then if the coil is wound in the form of a cylinder, it is called as solenoid. Okay, you can see here, you can see this picture 13.10. See, whenever the current is switched on, the ends of the coils is connected to positive and negative. That means it is connected to a battery and it is switched on. What happens whenever the current passes through a conductor? It produces magnetic field. Already we know this concept very clearly. So here also, whenever the current passes through a conductor, it becomes a magnet. That means it produces magnetic field. Clear? And you can see the magnetic field, how the magnetic field is inside the solenoid. It is like a parallel line. See, you are able to see this, right? It is a parallel line inside, and everywhere from from starting to ending, the uniform it has got the uniform magnetic strength. Magnetic field is similar inside, is same inside everywhere throughout, because it is a parallel lines inside, and the magnetic strength is same from left to right and top to bottom. Okay, that is one important thing about the uh, solenoid. So it is a uniform magnetic field inside the solenoid. And see here, for example, is a solenoid is connected. What is solenoid? It is nothing but number of loops, circular loops connected to a source. What source? It is not connected to a source, it is connected to a, it is connected to a galvanometer, because there is no battery here. If it is plainly, it is given, it is a galvanometer. What is the function of a galvanometer? The function of the galvanometer is just to detect the current. It just says whether the current is flowing or not. It doesn't measure the current. So see here, in the loop coil, and what is this N and S? Obviously it is a magnet. Okay, bar magnet. When the magnet is kept inside, it is pushed inside, what is happening? This deflection you are seeing here, it is, instead of straight, it is slanted. That means the needle has deflected towards the right left side. And you're seeing here, and if you're going to remove the magnet from the inside the solenoid, what is happening? It is the direction of this one is changing. Why? Because the magnetic field is changing. Earlier, the magnetic flux was flowing from left side to right side. That's why the deflection was on left side. Now the magnet is coming outside. That means right side to left side, and the deflection will be on the right side. Very, very, very simple. All concepts are same. Just the application will be different. That's it. And you need to understand very easily. And coming to this, what is happening here? What is inside? The black thing, the black or gray thing inside is a steel rod, plain steel rod. Why it is kept inside? I'll tell you. See, take a cardboard, and wind the insulated copper wire in the form of a coil and connect it to a battery and switch on. What happens? The it, the mag the solenoid becomes a magnet, and if it becomes magnet, what should be there? Magnetic field should be there. So if you keep the steel rod inside the solenoid for some time, more than half an hour or 1 hour, what does it become? The magnetic field lines would have passed through the steel rod also, and steel rod also will become a magnet. Once you switch off the solenoid and take this steel rod outside and bring some iron pins near it, it will get attracted to the steel rod. Why? Because steel rod would have become a magnet. What kind of magnet? Electromagnet. Why the term electromagnet? Electromagnet means, electro means electricity. Because of electricity, this has become a magnet. Through what? Through solenoid. So that's why it is called as electromagnet. Clear? Coming to this left picture, you can see here, See, current from left to right. See, if it is going from left to right, you can see the direction of the red needle here. It changes. It changes, right? It changes. Always it goes along with the north pole only. You can see it is always moving from right to left. And if no current is there, will the needle deflect? You can see here. No. See, the needle is not deflecting at all. And here current from left to right, you can see it is changing. It is rotating in a clockwise. And if you change the current from right to left, you can see here, the direction is totally reversed compared to the left, the current flowing from the left direction. So whatever you learned here is just an animation is shown here. That's it. Force on a current carrying conductor in a magnetic field. See, for example, take a battery and the switch is here and connected to a aluminum rod. Take an aluminum rod or steel rod. In this experiment, take a aluminum rod AB and tie it to minus, and this plus should be connected to a switch. Arrangement be like this. And what is this? NS is a horseshoe magnet. This is the shape of a magnet. Bar magnet you have seen in the previous slides, and this type of magnet is called as horseshoe magnet. Why horseshoe? Because horseshoe also will be in the same form. Okay, so that's why it is called as a horseshoe magnet, U-shaped magnets, where north pole is here, south pole is here. And you just suspend the aluminum rod inside and you switch on. What happens? The current starts flowing from positive to negative. And what happens when a current flows through a conductor? The conductor becomes magnet. And already the horseshoe magnet is there, permanent magnet. And since it is attracting towards south, that means this one is north pole. That means the north pole is created here. So because of the current flowing in the conductor, this becomes a magnet, north pole, south pole. So that's why it gets attracted. See here, north pole and south pole just got attracted here. And now you see the battery direction here. This is been connected to a switch. Now we change the position, interchange both. See here, and now this is connected to switch. That means the direction is changed. Now here, from here, the current passes and it goes here and it comes here. What happens? This becomes north pole and this becomes south pole, because whenever the current flows through a conductor, the conductor becomes magnet and it has got magnetic field. Magnetic field means it should have the direction, it should have the poles. That means it becomes south pole and this side it will become north pole. So you can see here the north pole and south pole has got attracted. That's why the rod gets attracted to the north pole. Clear? Right? How it works? This is the arrangement. North pole, south pole. So the magnet is there and A, B, C, D. This is the conductor and it is connected to split rings. Ring means it should be total circle. Split means, so you can see it is broken here. That means half portion is here and half portion is on the right side. So that's why it is called as a split ring. Okay, and the wire is connected to split ring positive side, and this positive side is connected to minus negative side. And what are these brushes? Brushes, when this axle rotate, the split ring also rubs and wears out because of friction and heat. So that's why the carbon brushes are given. And the other function of carbon brushes is, carbon brushes acts as a lubrication part, and also carbon brushes is a good conductor of electricity. So during the rotation also it passes the current to the conductor A, B, C, D. That is the function of it. Please listen very, very carefully. This is an important concept. So whenever the current is switched on, what will happen? ABCD becomes a, whenever the current flows through a conductor ABCD, it becomes a magnet. That means it will have magnetic flux. That means it will have north pole and south pole. So when north pole of this and north pole of this magnet comes, what will happen? It will ripple. Ripple means it will rotate. See here, you see in the right side picture what I'm showing. See, if the direction of the current changes, this direction also changes. See now it is rotating anti-clockwise. Now if it is changed, it rotates clockwise. That is the beauty of the electric motor. For electric motor we have to give the power, then only the axle will rotate. Correct. It happens due to the electromagnetic induction. And you can see here the same thing. If you cut open the motor, what will be there inside? You can see the brushes here, carbon brushes. Here also see brushes here. See, this is the function of the brushes. And where is the split ring? Here you can see here inside is the split ring. Okay, and ABCD, here is the conductor, and here one inside you can see the wire which is wound is called as a rotor coil. Rotor coil is called as a conductor. Okay, and this shaft here, and this is called as axle here, and magnets is here, that is called as a stator, and here also it is magnet is available. So everything is correlated. This is how the motor rotates. And this portion is called as armature. What is armature? The soft iron core on which the coil is wound. Coil means the copper wire is wound, plus the coils, you can see all the coils here, is called an armature. Okay, it's called an armature. Clear? The same thing, the same. I'm showing the picture. This is the electric motor, and see, continuously if you give the current, how what will happen? Because of magnetism, it ripples. You can change, you can see the color is changing from red to blue, blue to red. Why? Because it is getting rippled. North north ripple, south south ripple, north south attract. Because of that attraction and repulsion, it starts rotating, and the speed depends on the amount of current what you give. You can see here also same thing. Correct. Hope you have understood how the motor works. Electromagnetic induction, already we have seen the same thing, right? This picture we have seen. See this picture, take a cardboard cylinder, onto that just wind a copper wire and connect to a galvanometer. What is the function of a galvanometer? Already I have explained. Galvanometer is an instrument that can detect the presence of a current in a circuit. That's it. It detects the current. It tells us whether the current is there or not. How? Just by deflection of the needle. You can see here the needle is there. Just it deflects. If it deflects here, small current. If it deflects here, more current. If it deflects up to here, still more current in left direction. And right direction also it can show the thing. You can see here this picture. You can see, say right side it is going up to 20, left side is going to up to 20. How? Because it's going inside, it is coming out, it's going inside, it will turn to right. If it's coming out, magnet is coming out, it turn to left, it deflects left side. That's it. Why? Because the magnet has got a magnetic field. See, whenever the magnetic field passes through the coil, current will generate. Whenever the magnetic field passes through the coil, see, magnet is going inside, magnet has got the magnetic field. You can see here, this is the magnet. Magnet has got the magnetic field, and whenever it goes, see, all the magnetic flux is passing through the coil. It cuts the coil, right? What happens? This deflects. You can see here the deflection is happening. Clear? See, when it's going back outside, deflection is on left side. So this is the electromagnetic induction. That means we are inducing, like injection, we are giving the injection to the body inside. So same thing is happening here. It induces the magnetic flux, magnetic force inside the conductor. So if magnetic force is there inside the magnet, what will happen? The electrons will start flowing inside the conductor. The flowing of electrons inside a conductor is called as electricity. Clear? that is electromagnetic induction. It is also called as Faraday's law of induction, because Faraday was the scientist who was doing all this experiment. Okay, and here also you can see a coil is wound and is connected to a battery here, and again on the same single common cardboard, hollow cardboard, you can just wind a coil and connect to a galvanometer. What happens? There's no current at all here, right? Here if you switch on, the current will flow here and it comes back, and this one will become a magnet. That means it will have the magnetic field. See here, same thing. Instead here DC we are giving, plus minus means DC current, that is direct current. Here we are giving alternating current, AC current. So see, whenever it comes here, what will happen? It becomes a magnet. Then if it becomes a magnet, that means it will have the magnetic field. See here, the magnetic field is here. What happens? The magnetic field is passed on to the adjacent coil. So adjacent coil, it gets activated and all the electrons will start moving inside, and deflection will happen in the galvanometer. See here, this is the galvanometer. See, clear? That is the induction. That is the electromagnetic induction. Hope you have understood this. And come to this point, this is the application of electromagnetic induction. So what is happening here? See, whenever the current is coming here through a coil, what happens? This is an iron core, and there is one more set of coil. This set of coil is called as primary winding, and this set of red coils is called as secondary winding. And for input at primary winding is given by the AC. You can give DC also. AC power is given here. What happens? It becomes a magnet, and the magnetic flux passes through the iron core, and here once that continuous magnetic flux is coming out, it activates this coil, and whenever it passes over the coil, in this coil the electrons will start moving. That means electricity is induced in secondary coil and output is given. Understood? It can give more voltage or it can give less voltage. Here it is giving less voltage. Why? Because you can see number of turns is more in the primary, number of turns is small in the secondary. That's why if you give 200 volts, you will get only 20 volts at the secondary. This is a step down transformer. Where you have seen this kind of transformers every day, you will be using that. Say for mobile, how do you charge mobile? Using a charger, right? That thick portion what you hold in your hand and plug it, that portion is called as transformer. From the transformer the wire is taken and given it to your mobile, so that is a transformer. Hope you understood. Coming to Fleming's right hand rule, we have seen just a right hand thumb rule or right hand rule, and Fleming's left hand rule we have seen, and Fleming's right hand rule we have to see now. See Fleming's right hand rule, what does it show? This shows the magnetic field, and this shows the induced current, and it shows the motion. That means whenever induced current is coming into picture, it is nothing but magnetic induction. Induced current is related with the magnetic condition, magnetic induction, and that means Fleming's right hand rule is associated with what concept? Magnetic induction. Why? Because induced current is coming into picture, that you should forget. Electric generator, how does the electric generator work? See, it has got N and S. What is that? N and S, magnet. And same here, ABCD is a conductor. Okay, and are you seeing any source here? No source here, right? We don't have any source, just it is connected to a galvanometer. Why to galvanometer? So just to detect the current. And you can see here the arrangement, rings. In electric motor what we saw, split rings. Here rings means it is complete, there's no cut here, no split here, so that's why ring 1 will be here, ring 2 is here. And obviously the brushes should be there. Why the brushes should be there? Brushes should be there to continuously conduct the current, and it is also acts as a lubrication, because always the brushes are made up of carbon brushes. Okay, see how it is rotating here. The same thing is shown on the right side. See, I'll take a pen here. See, the same thing is shown in right side figure. Very simple picture. See, whenever it is rotated, that means whenever this one is rotating, the current is passing through it. The deflection happens. How it is happening? See, if you connect with the help of a shaft, okay, automatically it doesn't rotate. Something has to rotate this ABCD. What is this ABCD? ABCD is a conductor. See, this one is in rectangle shape. This is an ABCD, that is a conductor, and it should be coupled with the engine. So this will be coupled with an engine. Okay, that is coupling of engine. Whenever you put diesel or petrol engine, this is a generator, right? So we have to use either petrol generator or a diesel generator. Then you start this engine. Whenever the engine starts, what will happen? This will start rotating this shaft. And again, this shaft will rotate this. That means it will rotate the conductor ABCD. So once the conductor rotates, what is happening here? You can see here the current is generated. How? Because see, north to south, north to south, north to south, north to south. Here the magnetic field is there between north and south. Correct? Magnetic field is there. So whenever the conductor or the magnetic field passes through the conductor, what happens? Electricity is produced. See, beautiful concept. Simple. Okay, or in between the magnet, if you just rotate the by hand also you can rotate, or you can rotate with the help of the engine, diesel engine or a petrol engine. What happens? Electricity is produced. You can see here it is slowly rotating. Clear? See, usually we go for what is the AC we are going to use at home? AC means alternating current. Alternating current we use is 50 hertz. What is Hz? Hertz. Hertz means frequency. You can see here frequency. We use 50 hertz. That means 50 cycles per second. Alternating current. What is alternating current? How much alternating current we are getting at home from the government? 220 volts. Then usually what is hertz? That is 50 hertz. Throughout India we use 50 hertz. See, 220 volts, 50 hertz. Different country uses different ratings. So we in India we use 220 volts as an AC. AC current is 220 volts. Then sorry, not current. AC voltage. AC voltage is 220 volts, and frequency is 50 hertz. Okay. See here, one more thing is important thing. An important advantage of AC or DC. What is AC? Alternating current, which you get at home, or DC. DC means direct current. Is that electric power can be transmitted over long distance without much loss of energy. That's why whatever the poles you see outside, electric poles you see, there will be wires. Okay, aluminum wires, which will be coming. So those aluminum wires will come from a very long distance. So it is very easy to transmit the power, okay, power over long distance using AC current. So that's why AC current will be passed. Then we can convert AC to DC or DC to AC later. If you come and see the power station, how the power station will be there? How the power station will be there? Have you seen, anyone has seen the power station? See, here is the burning of coal will happen. Burning of coal will happen there. Then after that the water is there. Water will start boiling and it will become steam. Steam will become super steam, very high super steam, and it will come and rotate the turbine because of pressure. And the turbine rotates. Turbine rotates what? Conductor ABCD. What I have seen in the previous thing. It rotates the conductor ABCD. Okay, and this is the magnet. You can see north pole and south pole will be there, correct? So whenever the conductor is rotated in between a magnet, in between inside a magnetic field, what will happen? Electricity is generated. See, the same electricity is taken here and it's given to pole. This is pole, and after it comes here and we combine means will not join together. If we join both, it will become short. That means it is insulated and taken inside house. So inside house we'll have wires which will be connected to rooms, halls, toilets, outside, balcony, etc. So this picture is very useful. Domestic electric wires. What is domestic means? House. At house, how the connection will be there? See, from the pole, this wire is coming, earth wire is coming, and you connect everything to the switch, and live wire is there. Have you seen in the electric pole how many uh, wires will be coming? Usually, three wires will be coming. Correct? One is earth wire, which is in green, and one more is live live cable or live wire, or we call it the power line. So power line will be in red. Okay, and other thing will be neutral. Neutral also will be connected to here. Clear? See, live wire is connected here in one direction and neutral is connected in one direction, and green color is earth wire. See, whenever the wires comes here, especially the live wire and neutral wire is taken in an electricity board. You see, in your house there will be electricity board. Okay, if you open that, there will be fuse will be there. Main fuse will be here, and from the fuse there will be electric meter, where the lightman will come and check it and give the receipt to you, right? You have to pay the light bill. So the light meter will be here, the electric meter will be here, and it is connected to a distribution box. Here also we'll have small fuses. See, it is this line is taken into room, and this line is taken into kitchen, and see, this one is taken into hall, where you have the so many plugs. So for each line there will be small fuses. If something happens, the fuse goes away, and it saves the home, it saves the room. Clear? And what is the voltage? 220 volts. See here, potential difference is nothing but voltage. How much it is coming? 220. What is the current rating for general appliances like fan, TV, computer? Everything requires 5 ampere voltage. And current rating for high wattage. Which are the high wattage? High wattage is nothing but geyser, AC, your fridge, and oven. Everything comes under 15 amp voltage. If you put the plug to 5 amps, what happens? The equipment burns away. Okay, you should not do it. Or ulta also, mobile charging should not be put to 15 amps. What will happen? The transformer will become heat and it will burn away. So you should take care of this. So this is very important diagram. They might ask for you to write in the examination. So practice it 5 to 10 times. To an end of this chapter, very interesting chapter. Only thing, you people should practice the concept. Whatever the whatever I taught you just now, go back to the video once from the beginning and pause it and practice each and everything. Then it becomes very easy for you people. Thank you so much for being with me for such a long time. It's my pleasure teaching you people. Have a nice day. Thank you. Bye bye. If you have any doubts, please reach out to me or the class teacher. We would love to help you out anytime. Thank you.